Okay, I think we can start. Welcome everyone, and it's my pleasure to introduce our speaker of today, Byung-Jun Min. He got his PhD in Korea University with Professor Go on complex networks. Then he moved to the City University of New York as a postdoc working with Hernan Maxe. And then he came to IFISC from September 2016 to February 2018 as a postdoc. And from here, he moved as an assistant professor, where he's now at Chungbuk National University in Korea. And he will be here for the rest of this month. So I think he's going to give us an overview of his recent work. But anyone willing to interact with him during this month, he is in the floor upstairs in the postdoc room there. Okay. So welcome and go ahead.
Okay, thank you for introducing me, and thank you also for giving me this opportunity to introduce our recent work. As Max introduced, I worked here about 5 or 6 years ago, and you can find the evidence in the 3rd floor of this building. There are picture of 2016, and you can find me. It's younger and thinner than now, but it's me. Yeah. Anyway, okay. Today I'm going to talk about contagion processes on complex network, especially implementing competition and cooperations. Okay, many real-world phenomena can be modeled by contagion processes, including epidemic spreading, computer virus spreading, or innovation rumors, or information propagation in our society. For this reason, many researchers have studied contagion or spreading processes for a long time. Maybe the earliest mathematical modeling of epidemic spreading was conducted by Daniel Bernoulli in 18th century. In his work, he was trying to model smallpox, which is now completely eradicated. And maybe the first modern type mathematical modeling of epidemic spreading was conducted by Kermack and McKendrick in 1927. They proposed a prototypical model of epidemic processes, which is, in a modern term, is a prototype of SIR model. And I would like to stress that these contagion models are strongly related to the models of non-equilibrium statistical physics. For instance, SIS model is essentially the same as contact process, and also SIR model, which I will introduce more detail, is exactly mapped into bond population problem. So epidemic model is maybe the simplest model showing phase transition and critical phenomena. So, okay, I would like to introduce 2 very simple epidemic models, because in the rest of my talk, I will talk about a kind of variant of these 2 models. First, I would like to introduce susceptible-infected-recovered, in short, SIR model. In this model, each agent can be one of 3 states: as susceptible, infected, or recovered. Susceptible S state represent healthy state and also subject to be infected, and I state represent infectious or infected state. So this state can infect its neighbor to be infected, and recovered state represent recovered or removed state. So in this model, if an agent recovers from a disease, then it can be recovered state and get permanent immunization from the disease. So in this model, there are two different dynamical processes. One is infection, the other one is recovery. Infection process is mediated by pairwise interaction between two agents. One is susceptible and the other one is infected or infectious. So susceptible agent becomes infected if susceptible individual interacts to an infectious one, and then S state becomes I state with a certain probability. And recovery process is different. Recovery process occurs totally autonomously, meaning that infected agent becomes susceptible state by itself. So in this model, in I state is an intermediate state. So in the long time limit, in our system, there can be only susceptible or recovered individuals. So in this model, we usually measure the fraction of recovered individuals as the size of epidemics, because R state means that individual was once infected, right? So this is the basic concept of SIR model. And the other simple model is SIS model. Maybe SIS model is simpler than SIR model, because in this model, there are only two stages, S and I stage. And the infection process is exactly the same as SIR model, but the difference is recovery process. If in the SIS model, if infected agent recovers from the disease, it becomes susceptible again. You can think of seasonal flu. For the seasonal flu, we can if we recover from flu, we cannot get permanent immunization, but rather we can get infected again on flu again. So this is their situation. So in this model, in the long time limit, there can be two phases. One is observing, or the other one is active. Or if there are only susceptible individuals in our system, that is the observing phase. And on the other hand, if there are a mixture of susceptible and infected agents, then this is active phases. So in this model, we usually measure the fraction of infectious or infected agent in the steady state, which is in the steady state, the size of epidemics, right? Okay, these two models, these two SIR and SIS model belong to the simple contagion. In general, contagion models can be categorized into two classes, simple and complex contagion. So simple contagion is composed of pairwise interaction, and historically is largely inspired by the spread of disease, the epidemic spreading. So the model that I introduced, SIR and SIS models, belong to this simple contagion. And there is another type of contagion model that is complex contagion. This complex contagion was originally developed in order to model the social contagion, like the spread of social behavior or social emotion, like social emotion, like that. So in the complex contagion, the contagion process is governed by collective interaction or group interaction between many, between all the neighbor of a given individual. So ground-vector model, ground-vector threshold model may be the earliest model of this type contagion. and also many other contagion processes like bootstrap population, watch threshold model, and generalized epidemic model belongs to these complex contagions. Let me clarify the difference between simple and complex contagions. Okay, here is two types of, here are susceptible and infected agent. In the simple contagion, this susceptible agent can be infected or can be adapted on new information by just a single exposure to this infected agent. On the contrary, in the complex contagion, this susceptible agent needs more than one exposure or more than a certain fraction of exposures are needed to be adapted new information in this case. So basically, simple contagion model is governed by pairwise interaction between two agents, but complex contagion is governed by collective interaction of all the neighbors. Okay, so simple contagion is, as I told you, pairwise interaction, and single exposure is enough to be adapted. And typically, simple contagion model shows continuous second-order phase transition between global epidemic and non-epidemic phase. On the other hand, complex contagion is governed by collective interaction, and multiple exposures are needed. And typically, complex contagion shows discontinuous transition. So our question here is that what happens if simple and complex contagion compete each other in a single network? So we'd like to model this kind of real world situation. Okay, look at this is an cascade. This is spreading phenomena in real world example. In 1913, there was a huge online campaign about equal human rights campaign. So in the more than 3 million Facebook users changed their picture, profile picture, in order to express the support to the human rights campaign. And fortunately, all the details of this propagation of equal sign movement was analyzed by Facebook researchers and also reported in this paper in 2015. Okay, here are really many interesting empirical observations, but we were actually found this interesting result. This figure shows the cumulative distribution as a function of adaptability. Here, adaptability is the number of exposures before change my picture. So here, specifically, the adaptability is defined by the number of neighbors that have the equal sign before I change my picture to equal sign picture. So as you can see in this figure, about more or less 10% of user changes their picture just after a single exposure to the equal sign neighbors. So about 10% agents follow simple contagions, but the others, more than 80% of users follow this complex contagion. So real world contagion process is neither simple nor complex contagion. in reality, simple and complex contagion are mixed in our society. Okay, so we introduce this heterogeneous adaptability. So some nodes in our network follow this simple contagion, so-called simple nodes, and the others follow this complex contagion, so-called complex nodes. So this is the example of our system. Here is a given network structure, and we randomly we choose a p fraction of nodes of complex nodes, here denoted by square, and the others 1 minus p fraction of nodes follow simple contagion, so-called simple node, denoted by circle here. This star is the seed of our contagion processes. So this is an example of our contagion model. Initially, all nodes are susceptible states except a small fraction of seed nodes. And then next step, this seed node or newly infected or newly adopted node attempt to transmit the new information with a probability lambda. Then the next step, these two simple nodes changes their state to be adopted because it received the new information from this seed node. But this node, this square node, received the new information from this node, but does not change its state because it is complex node. So this node needs more exposures to be adopted. In this example, the number of exposures for complex contagion is 2. So complex node needs 2 exposures to be adopted. And next step, these newly adopted nodes try to transmit this information to their neighbors. And then this node received twice this new information, and then this node becomes adopted. And then we repeat this process until there is no newly adopted nodes in our system. Then we measure the final fraction of adopted nodes in our network. So here are some important parameters. P is the fraction of complex nodes. N is number of exposures for adoption of complex nodes. And lambda is the probability of transmission, probability of successful transmission. And rho is the fraction of initial seed nodes. Oh, sorry. Here is the, okay, we solve this problem by using mean field equations, mean field approximations. So we get these phase diagrams. This is the phase diagram for any 2 case. Here you can see the transition line here. But this transition line is given by the transition point for solely simple node. So we, as the typical contagion model, we found 2 phases: adoption, global adoption, or non-adoption phases. And there is the transition line. But interesting point is that if the fraction of complex node exceeds a certain point here, then the transition becomes discontinuous. So if the majority of nodes follow complex contagion with n is 2, the transition between non-adoption and adoption phases becomes discontinuous, like a complex contagion. But below this point, the transition is continuous, like the usual simple contagion. if n is larger than 2, the situation is more interesting. Here is still the continuous transition line, but we have, but the discontinuous transition lines are separated from this dashed line. And all the discontinuous transition, all the second transitions are discontinuous. And the location of the second transition depends on the number of n, right? So we found two transitions for a given n. First one is continuous one, and second one is discontinuous one. So what happens for this n is larger than 2 case? Okay, here is, for instance, n is 4 case with different p values. So if we pick p and increase lambda, then we will get, like, for instance, p is 0.2 case, like this transition, right? So we will get only one continuous transition here. But if p is larger than this tricritical point, then we will get two consecutive transition points. First one is continuous here, and the second one is discontinuous here. So we will find these double phase transitions. So what's the mechanism of this double phase transition? Below this lambda, okay, this figure shows that, okay, the p is 0.8 and n is 4 case. And blue nodes are complex nodes and red nodes are simple nodes. And dark blue and dark red are adopted states, and light red and light blue are non-adopted states. So below lambda 1, we found that both simple and complex nodes are not adopted. But if lambda is larger than lambda 1, then some simple node starts to become adopted. And above this second transition, both complex and simple nodes become adopted. So we found this intermediate phase where simple nodes becomes adopted, but complex nodes remain a susceptible, non-adopted state. Okay, we also checked the competition between simple and complex contagion with SIS type recovery process. So in this case, the model is the same as previous one, but infected individual can become susceptible state with a certain probability at each time step, right? So we found a very similar result as previous one. Maybe you cannot find the real difference between this one and previous one. Anyway, and we also found the double phase transition with the p is 0.75. And the mechanism of this double transition is the same as previous. Here you can this red curve represents the fraction of adopted simple nodes out of total simple nodes, and this green one represents the fraction of adopted complex nodes out of complex nodes. So in this intermediate region, we still found that simple nodes are adopted, but complex nodes still remains the susceptible stage. Right? In addition to this double phase transition, we also found this hysteresis in this SIS type dynamics. If we increase lambda from the low value, then the final fraction of infected agent follow this blue curve. And here is the first transition, and here is the second transition. And then after above the second transition, R reaches this high R phase, highly infected phase. Once the system reaches this highly infected phase, and we try to reduce this lambda, maybe by imposing social distancing or like that. And then this, even though we decrease lambda from this value, but the system still remain this highly infectious phases because of the complex nodes. So we found this hysteresis region, and in this region, complex nodes can maintain the adaptive state by themselves. So we found that complex contagion is hard to spread the disease, and also harder to mitigate once it reaches the highly infectious phases. Okay, next we study the cooperative epidemics on a network. So here our question is that what if more than two interacting pathogens spread simultaneously on a given network? As we know, there are so many diseases simultaneously active in our society. For instance, here is yellow and blue one. If these two pathogens are independent each other, then problem is easy. Just we can think each pathogens treat as independent pathogen. But if our question is that if two pathogens interact each other cooperatively, then what happens in the final state of epidemics? The examples of these cooperative epidemics in real world is the HIV and tuberculosis co-infection. As we know, HIV weakened the immune system, so it increases the risk of active TB. For the TB, if the TB is inactive state, it is not infectious. But if TB becomes active, it becomes active. So HIV and TB cooperatively infect. HIV and TB affect cooperatively each other. There is another example. This is COVID-19 and flu. This phenomena did not happen in reality, but many people were worried about this twindemics last winter. If these two COVID-19 and flu outbreak simultaneously, then there can be some more dangerous mutation of COVID-19 or flu as well. And even though these two diseases don't interact each other, but if these two diseases outbreak simultaneously, then because of the limitation of capacity of healthcare system, there can be some more. These two diseases can be more dangerous than just a single one. So we need to study this cooperative epidemics. Okay, let's think about very simple setting of cooperative epidemics. We consider only two diseases, A and B, and we consider these two diseases spread simultaneously. So there can be 4 active phases or active states S, A, B, and AB. Here A and B represent this node is partially infected, meaning that this node is infected by A but not B, and this node is infected by B, but not A. But this black nodes, AB, represent this node is infected by both A and B, so that this node is infectious for both A and B. So if a node is singly infected, the dynamics is the same as the usual SIR dynamics. Okay, here is the full dynamical rules of our model, but I will not go to the detail because it is complicated. But I just put this rule because I just say we consider all the details, all the possibilities. So anyway, the essence of our model is that here, if this node is infected by both A and B, then this black node, AB node, infects its neighbors with the increased probability Q. So the cooperativity is implemented in here Q. So we consider cooperative epidemics. So Q is always larger than P. So for instance, this black node, okay, so we define the degree of cooperativity as W. W is Q over P. So if W is 1, meaning that there is no cooperativity, so that A and B spread into our society independently. But if W is larger than 1, there is some degree of cooperativity, right? So here is an example of our model. Okay, initially all nodes are susceptible, and we employ a certain fraction of seed node A and B here, and then susceptible nodes becomes infected with the probability P, right? Like usual SIR dynamics here. And here, these two pathogens meet, and then this node becomes doubly infected by A and B, and then this node infect its neighbors with increases probability Q, and this node also doubly infected. Then this node infect its neighbors with probability Q, which is larger than P. So we attack this problem. Okay, I would like to say that cooperative epidemics was studied many other researchers, and with a very similar setting. But the main point of our work is that we try to solve this problem by using this message passing equations. Message passing method was originally proposed to solve disordered spin systems, but it can also apply to the epidemic problem. Here is an reference. So the essence of the message passing equations for epidemic model is that we introduce this probability U. Okay, here is some typo, and we introduce probability UBA. That is the probability that B does not receive a message, in this case disease, from A. This probability can be expressed in terms of the probability between these neighbors and A, except this B, like this one, because 1 minus the complementary probability is given by 1 minus the product of this probability times P. Then by solving this equation, actually for the full network, we can write down this self-consistency equation. And by solving this equation, we can find the fixed point of Uij's. Then obtaining this Uij, we can obtain many interesting measurements like final epidemic size or epidemic probability, like that. The strong point of this message passing technique is that it can use for a small size network, and it can deal with quantitative disorder of network directly. And more importantly, this method can allow us to analyze the epidemic process on each node level, not on network level. So this is the strong point of message passing techniques comparing to typical mean field approximations. But there is also a weak point. Weak point is the computational cost. We need to solve two L equations simultaneously, which is much more harder than mean field approximation. Typically, mean field equation, we need to solve only one single self-consistency equations. But so anyway, we developed the message passing theory for the cooperative epidemics that I introduced before. So this is the self-consistency equation of message passing theory. So here is this Uij is the probability that I defined before. Here we can see two terms. Briefly say the first term represents the infection probability from doubly infected nodes, and the second term represents the partially infected partially infected nodes. So here is only Q, but here we have Q and P. So if Q is the same as P, this equation becomes the ordinary message passing equation for ordinary SIR model. And expanding U near the one, we can find the epidemic threshold. Okay, so by solving this message passing equation, we found this phase diagram for ER networks. Here is we found there are two phases: global epidemic outbreak and no outbreak. If the P is larger than a certain this PC, then there is the global epidemic outbreak. As you can see in this phase diagram, the cooperativity does not affect the PC. But if we increase cooperativity here Q, then transition nature changes from continuous transition to discontinuous transition. So look, this is the schematic schematic expression for the fixed point. Here, PC is always same here, but if Q is larger than WC, the transition changes from continuous one to the discontinuous one. Okay, and as I told you, our message passing techniques allows us to analyze the epidemic spreading on each node level, right? So we also try to calculate the probability of epidemic outbreaks for a given pair of seed nodes, one for one for disease 1 and the other one for pathogen B. So in this case, we choose a pair of seed nodes, one for disease A and the other one is the other one for disease B, and we calculated numerically and analytically the average probability to bring out the global epidemic for a given set of for a given set of seed nodes. So as you can see, the theoretical prediction and the numerical simulation gives the perfect agreement for ER scale-free and with the different cooperativity. So this measurement tells that which seed node is more influential than the others. So we can find by using message passing equations the influential spreaders in the cooperative epidemics. So by using message passing equation, we reveal how to identify influential seed nodes in our networks. Okay. Okay, we consider contagion processes incorporating cooperativity and competition between simple and complex contagions. For the competition, we find a rich variety of phase transitions, and most importantly, we found double phase transitions and hysteresis. For the cooperative epidemics, we introduced message passing equations and found abrupt phase transitions, and also we proposed a method to identify influential spreaders, influential seeds in cooperative epidemics. Okay, here are some references. So some references that I gave in this talk. Okay, so finally, I would like to thank to my collaborators, Jung Jae-kook, Jie Che in Chungbuk National University, in my lab, and Claudio Castellano in Rome, and also Maxi San Miguel here. Yeah. Thank you for your attention.
Thanks very much, Byung-Jun. So we have now time for questions. If there are, we can start from the people here in the lecture room. Anyone? Question? Comment? Emilio?
Are the exponents you find for three critical points and these sort of things are in some known universality classes of equilibrium systems, or are different, or what can you say about them?
You mean the okay? I mean here, right? It's the this one, right? This is a typical mean field critical exponent for tri-critical pointing. So all the exponents are typically appear in mean field case.
Yeah, but you are solving this in mean field.
Yes.
Have you done numerical simulations to compare with that?
I haven't checked that numerically, but I guess there is no reason to different from no reason that the critical exponents are different from the mean field exponent. I don't know.
Even if the range is so I assume you are only considering one type of connections and between neighbors, isn't it? Or do you check different types of networks?
Well, if we introduce okay, this all the exponents are derived for ER type networks. If we introduce more like a scale-free network, then the critical exponent should be different. But well, the answer for now is that we did not check the exponent numerically. Yeah.
Okay, thanks.
You mentioned that you find both double transitions and hybrid transitions. Can you explain which is the difference between the two?
Okay, here the term of it's just the terminology. The hybrid phase transition is typically we say the here okay for the typical discontinuous position in equilibrium system, there is no critical behavior, right? The critical behavior appears only in continuous transition, but in this case, there is a discontinuous jump and also critical the critical behavior like this one. So in this case, this kind of phase transition is called by hybrid transition. The double transition is as I told you, this kind of two conjective transitions appear by changing one control parameter.
So this particular transition doesn't have critical behavior. Is that
Yeah, here we have critical behavior. So this continuous transition is hybrid one, hybrid phase transition, and these two transitions are double phase transition. I mean, this transition is continuous one. Yeah, this is hybrid one. And
More questions? Before asking if someone online wants to ask a question, I have one myself. You mentioned that your method, when you have this cooperativity of infection, will not work for complex contagion. But is there any study of this cooperativity in processes of complex contagion numerically or?
Yeah, there are many. There are not many. No, there are some. Yeah, I mean, for maybe one of the this group studied cooperative epidemics for a long time, so they did many numerical simulations and they reported discontinuous transition like that, this phenomena, similar phenomena. But here I say it's hard to apply to complex contagion is for message passing equation. So message passing approach is hard to apply complex contagions because we need to calculate all the combinatorials in this calculation. But as long as I know Gleason and Mason Porter tried to at least mathematical formalism, try to give a mathematical formalism for message passing equation for complex contagion, but it is practically harder to apply because, as I told you, we need to compute all the possible combinatorials.
Okay, thank you. Now, if there is anyone online that wants to ask some question, just go ahead and mute yourself and speak up. No one there? Looks like we have no questions from the people online. Okay, so no other question here, no comment. So again, thanks very much.
Thank you.